So again, here's the title of the notes. We're just going to figure it out. And the way we're going to do this is not with me talking, because I'm tired of talking for you guys. We're going to kind of work through them on our own and then come back together to make sure we all agree. For 12 functions, we're going to set up something that looks like this. We're going to be talking about the domain, the range, the symmetry, the boundedness, asymptotes, discontinuity, increasing and decreasing intervals, their extrema pieces, and their end behavior for 12 different functions. We're going to do the first one together so you can kind of see how to answer these, and then you're going to try to answer the 11 other ones on your own, and then we'll come back together and we'll clean up our notes to make sure that all of our notes are correct. So the first basic function that we have is everybody's favorite basic function, the linear function. The linear parent function is f of x equal to x. Now we can set up a bunch of tables and get values, but you also have a piece of technology that can do that for you. So for this one, we're going to plot 5 different points to draw a really good line on our notes. So on your calculators, you can type y equal x and then go to the table. And so instead of the graph, go to the table. We're going to take some of those coordinate points and we're going to plot them on our piece of paper nice and neatly so we have a nice looking parent function. Once we have the coordinate points from our table on our calculator, we can plot them. For this one, we're going to plot 5 different points, which if I plot the points that I got out of my graph, that would be -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. You can obviously tell what's happening here, and so if we draw our graph, doing our best to do a straight line, I know I didn't give you rulers, do your best, they're just your notes. We have our linear parent function. Now we discuss the different properties for this parent function, starting with its domain. Domain is describing the graph x-axis, or from the left to the right. What's happening on the left side of this graph? Oh, it's going down, but look side to side. Is it stopping at any particular number, or is it going out to infinity? Infinity to infinity, so the domain is all real numbers. Please use interval notation or the fun and funky R. -infinity to infinity, which we also know because it's not one of the 3 functions with a restriction on its domain. We could have just answered this one right away. For range, now we look bottoms to tops. Those arrows are going from -infinity to +infinity as well. So there's the domain and range for this linear function. Symmetrical wise, is this one even? Can I fold it along the y-axis and it land right on top of itself? No. Is it odd? Can I put a pin in the origin and then rotate it around and it land right on top of itself? Yes, which means that this is an odd function. It's symmetrical about the origin. Boundedness talks about maximum, like a highest point and a lowest point. Does this have a highest or a lowest point? No, so it is unbounded. Has no boundedness. Does it have any vertical or horizontal asymptotes? Well, remember, those are things that it can't touch. Were there any breaks in my domain for any reason? Or any breaks in my range for any reason? No, so we have no asymptotes for this graph. Did I ever have to pick up my pencil when I was drawing the line? It's a continuous function, so it has no discontinuities. Where on its domain is it increasing? If you were walking across this graph, would you ever actually decrease? No. You'd increase the whole time, right? So its entire domain is increasing from -infinity to infinity, and there's no points that it's decreasing. Kind of going with the boundedness, are there any extrema pieces for this graph? No, it has no maxes or mins, so again, we get to say none for that one. But then we get to talk about its end behavior, and we're going to do so in a limit statement. two limit statements because we're going to do one side on the left and then one side on the right. So the end behavior here, and I'll scoot it up because I know it's kind of hard to see if you're behind somebody's head. We're going to say the limit as x approaches negative infinity. So we're looking at the left arrow of this function f of x. What direction is that left arrow headed? Down. So we would say negative infinity. Then we repeat the limit statement, this time changing it not just to negative infinity, but positive infinity. Where is that arrow headed? Up, so we would say infinity. Sometimes that's a number. Sometimes the left arrow is headed towards like the number 1 or the number 0. But we're looking on the left side and the right side for what's happening to those arrows. So that's the linear graph. So on the next 12 slides, essentially, you're going to see a computer-generated version of each one of these that you could have for the 12 basic functions. It's going to start again with linear, because it'll be better handwriting than mine, but it's going to go through how you would answer each of these for the 12 different functions. Most of the slides I'm not going to narrate at all because they're pretty straightforward, but some of them I'm going to stop and narrate, so there won't just be a 5-second silent slide on there if there's something interesting and different about that function. So just pause the video when you need it to write down all the things about the function. If you have questions about why that is the thing, come ask me in class. So we'll talk quickly about rational functions because they have a lot going on with them. First thing you notice when you're graphing it is that there is a horizontal asymptote as well as a vertical asymptote. Remember that denominators cannot be equal to 0, so there's always going to be a gap in my domain here at 0, or whatever the denominator equal to 0 is, creating this vertical asymptote. Additionally, because it's a rational function, we do Bobo, Botan, or Betsy. And since this is a Bobo, bigger on bottom, it also has a horizontal asymptote or end behavior of 0. Okay, so you can kind of see that reflected in the domain and the range. I also wanted to point out that there's an extra symmetry for rational functions. Not only is it symmetrical about the origin or an odd function, it's also symmetrical about the line y equal to x. This is another type of symmetry we didn't really discuss this year in this class, but if we were to draw a diagonal line y equal to x across this graph and fold this rational function along it, it would fold right back on top of itself. So that is another type of symmetry there that we hadn't really discussed. So I just wanted to pause there since this has some differences from rational, cubic, and quadratic functions. The only thing I really want to talk about for this one, because a lot of it makes sense, is the end behavior. If you notice, the left end behavior does not say as it goes to negative infinity, because it does not go to negative infinity. So when we talk about the left end behavior for this, we're actually going to use this notation here that says as x approaches 0 from the positive side, because it doesn't approach 0 from this negative side. It only approaches 0 from the positive side. So again, it does not approach on the negative side of 0, but it does approach 0 on the positive side, which is kind of a confusing topic. We will talk more about that when we get into limits, when we get to calculus concepts. But for right now, just know that since this end behavior or the graph itself doesn't go to negative infinity on the x-axis from this domain here, stopping at 0, that the end behavior also doesn't go to negative infinity. It goes to 0, but only from the right side. pausing to narrate this as well. Just like with square root functions, we don't go to negative infinity since the domain doesn't go to negative infinity. It only goes close to but not touching 0, which again is the limit as x approaches 0. So this end behavior is similar to square root in how you write it. However, this time it doesn't just stop at 0, it goes towards negative infinity as we get closer and closer to 0. So the step function, or the greatest integer function, is a really interesting looking function because what it's doing is it's taking every x value, like if I was at 0.5, and raising it up to the next largest integer, which is 1. And all of these are going to be 1 because that's the biggest integer until I get to 1. And then the next largest integer is 2. And so for an x value of 1.75, it would come out as 2 because that's the greatest integer. Really weird function, and lots of weird things happening with its function, including its range. Its range, since these are all disconnected right here, we have a bunch of points of discontinuity along this graph at literally every integer. Its range is not going to be written in interval notation. You would just say that y is an element of the integers. So this weird looking e is element. Again, mathematicians are lazy. We make up symbols for everything. Y is an element of the integers because only outputs I have are the integer outputs. It's technically unbounded because it doesn't have a lowest or a highest value, but the discontinuities in it are infinite because every single integer, there is a non-removable discontinuity. So there are infinite non-removable discontinuities at all of the integers, which also means that its extrema, it has lower or higher extreme values, maxes and mins. There's infinitely many, and they're all occurring again at those extrema. But oddly enough, the end behavior is similar to linear. As you go towards negative infinity, that's going to get closer to negative infinity. And as you go to positive infinity, the graph is going up, so it's going towards positive infinity. Yeah, there's no arrows here, but if you keep following the graph up and out, it's going to continue kind of like a linear function in its end behavior. But it has all of these infinite non-removable discontinuities, again, at the integers. I just want to say this, that before you panic about this function, the logistic function, it's used in a lot of modeling for business and different things like that, but it is a basic function, but it is not a commonly used basic function, especially in this class. So don't panic about the way that it looks, but I just wanted to point out that its range is only from 0 to 1, that these graphs, these asymptotes here, the line is going to get really, really close to but never touch both a bottom and a top, which means that this is a bounded graph. It's the first time we've seen that. Bounded both above and below, which is cool. And then we have sine and cosine. Now, sine and cosine we're going to dive into in the second semester a whole lot, not as much in the fall, but its domain is all real numbers because its graph can go on for forever side to side, but it's only going to bounce back and forth or oscillate between -1 and 1. This is an odd function because if I put a pin right here and rotated it around the axis, it would land right on top of itself, but it's bounded because it has highest and lowest values. Now, it doesn't have any asymptotes or discontinuities, but we're not even going to talk about its increasing and decreasing intervals. I'm glad that maybe you tried, because like from here to here, it's increasing and then decreasing, but then increasing and then decreasing. And we'd literally have too many intervals to talk about, so we just don't talk about increasing and decreasing intervals for sine or cosine. And because it has so many maxes and mins, since it's oscillating back and forth in between them, we just say that there are infinitely many extrema, all local maxes and mins, but we don't name them because we'd have to keep naming them for like ever. And then the same sort of thing is going on for cosine. Again, bouncing back and forth between -1 and 1 inclusive, which means I actually touch -1 and 1. This one, though, cosine, is symmetrical about the y-axis, which means it's even. And then the rest of it is pretty much like sine. It's bounded above and below because it has a designated range above and below. And there's too many intervals of increasing and decreasing because every time you turn and make a new wave, you have a new increasing, decreasing part of it, which means also there are infinitely many extrema. Now those are the 12 basic functions, and I know that that's a lot, but again, just having the properties down and discussing the properties of these different functions solidifies not only the 12 basic functions, but also what those properties mean and which functions might have them and which functions you don't have to worry about them for. I know this was a long day and a long video. Thank you for sticking with it the whole time.